Okay, almost every engineering project involves some sort of material. And the question is like, how do you choose the right material for the project? So there's certain factors that go into this. Typically, the first one that you always look at is cost. Uh, you don't want to use gold when steel will do. Don't want to use steel when plastic will do. That kind of stuff. Two is how available is the material. So, uranium is a material that has lots of great properties, but it's not very available. If I look around, I can find like wood just about everywhere. So that's a thing. These two things tend to have some relationship, cost and availability, but not always. The question also is how does this affect the environment? Right. So like a big concern in like paint products is things like, if you put lead in the paint, then the people around are going to get sick. Or if I use carbon as a fuel, we're going to be adding to the global warming problem. So, if I'm going to be dealing with something where I'm going into the water, I don't want something that's going to leach chemicals into the water and kill the fish. So these are environmental questions. Uh, Chemical reactions. Okay, so all materials are chemical. Some react with others. These are things like the Statue of Liberty is made out of copper, but it's green because it's reacting with the oxygen in the air. And steel, like you can use it to build something, but it rusts. Or you don't want to use something that's highly soluble if it's going to be underwater because it'll just dissolve. So these are questions about chemistry that come into materials. Physical properties, right? So these are things like you would study in physics class, like mass, volume, density. We'll get into that in a little bit. And then we have also what are called mechanical properties, and we'll do a bit of a deep dive into that because these are things that are not commonly discussed in other courses. So, 6 factors that go into material choice: their cost, the availability, the effect of the environment, how do they react chemically, what are their physical properties, what are the mechanical properties of that material. Okay, so physical properties of a material are things that you commonly discuss in physics classes or most general science classes. Things like mass, how much stuff is in a thing. Like if I put it on a scale, how much mass does it have? Volume, how much space does it take up? Density is kind of a combination of these two things. This determines all kinds of things. So it's how much stuff is in a certain amount of space. But like density can ask questions about like buoyancy. If the density is less than 1 cubic centimeter or 1 gram per cubic centimeter, then something floats in distilled water. If it's more than that, it sinks. So these are things that come up. And a physical property also includes color. The color of something is a very physical reality. It's an optics kind of thing. So sometimes color matters in your design. So color is a physical property of a material. All right, so the next thing we're going to look at is mechanical properties. So mechanical properties are where it's not right. Mechanical? No, mechanical. There we go. Mechanical properties are kind of where the engineer and technologist really have to dig in, okay? And we've got a whole list of things. So we got one called tensile strength. And this is like if you take something and you try to pull it apart, how much force do you have to use in order to be able to pull it apart that way? Yield strength. Yield strength is how much force do I have to use in order to push on something in order to deform it. So like something like lead or gold has a low yield strength. If you push on it, it bends fairly easily. Something like steel has a high yield strength. If you push on steel, it's not going to move much. Okay, materials for a particular job have a fatigue limit. So, like, think about like the filament in a light bulb. How many times can or how long can I burn that filament in the light bulb before it stops serving its purpose as a tungsten filament? Or like the rubber in a tire, how long can I drive on that tire before the tire fatigues and eventually will no longer serve its purpose safely? Impact strength is another mechanical measure. Impact strength is how hard can I strike an object. So imagine instead of like pushing with your thumb in yield strength, it's like how hard can I hit it with a hammer before it shatters or before it breaks. We have a thing called flexural strength. Okay, so flexural strength is like if I build a container out of it, how much pressure can I put on the inside of the container before it ruptures? Okay, so like let's say I build a wood bowl, how much pressure can I push into that bowl before it ruptures, as opposed to like a steel bowl, which will probably deal with that much better. Ductility, that's a great word. Ductility is basically like how much can I flex something or bend it before it breaks? So like a pencil is not very ductile, okay? But duct tape, you can flex that stuff all day. It has a high level of ductility. Okay. Compressive strength. With a P. Compressive strength. Okay, so this is like kind of like the opposite of flexural strength. In flexural strength, you're pushing out from the inside to see when it's going to rupture. For compressive strength, you're pushing in from the outside. So imagine like taking like a piece of concrete and how much pressure can I exert on that concrete going inward before it shatters into little tiny pieces, right? So this is what we mean by compressive strength. Another one that's a mechanical property is actually roughness, right? So this has to do with like if I take something and I rub it against something, right? It'll generate heat. So the faster it generates heat when I rub it against something, the rougher it is. Fracture toughness. Okay, so this is a tough one. This is once it has a crack in it, how likely is it to crumble? Okay, so think about this. Like once it has a crack in it, how likely is it to crumble? So like once it's been fractured, does one fracture do it? And is that enough to make something completely fall apart? Now, some things are better at being broken in small ways and still maintaining their shape, where other things are not. Like a window is tricky because like ordinary glass, if you crack it, it tends to shatter. If you crack a windshield on a car, which is a special type of glass in the way that it's manufactured, the crack can stay in that windshield for quite some time without having the windshield shatter. So like car windshields have a high fracture toughness. That's kind of an interesting measure. There's something called shear strength. So in shear strength, this is like you're putting a load on an object, like a bridge or the ceiling, and it's how much does it give. Like if I put a load of a particular mass on like the ceiling beam above you, does it stay straight or does it give a little? And the more it gives, the less the less strong it is for shear, right? So it doesn't break, but it's a matter of how much is that object giving when it's taking a load. So like if you walk across the floor that has a low shear strength, like maybe the bridge between Marshall Offutt and the library, you feel that bridge give a little bit. That's an example of shear. Whereas if you walk across the floor within Marshall Offutt, the floor doesn't give at all. So that floor has a high shear strength. Resilience. All right, so resilience is actually a measure of absorption of energy. So you, let's say something gets struck by a ball, and it absorbs the energy of the ball, and the ball just falls flat on the ground. Right. So imagine like hitting a beanbag chair or something that's like highly elastic with a ball. That thing is going to absorb the energy from the ball and then just fall. So that's a highly resilient object. Whereas something like a baseball bat has a low resilience. It doesn't absorb much energy from the ball at all. That's why when the ball hits it, it flies off, right? So something that's somewhat hard is going to have a low resilience, because either the bat is going to cause the ball to redirect or the bat's going to break, right? So that's a low resilience. Something that has a high resilience can absorb a lot of energy from something like a catcher's mitt or some sort of like rubber memory foam. Can take a lot of energy, absorb it, and then not push it back or project it out. So these are your mechanical properties, a whole list of them there: tensile strength, yield strength, fatigue limit, impact strength, flexural strength, ductility, compressive strength, roughness, fracture toughness, shear strength, and resilience. So this is on top of the physical properties of mass, volume, density, and color. The chemical interactions, when you put two substances together, what happens with them. And then finally, things like environmental effects, the availability of the material, and its cost. These are all things that you take into consideration when you choose materials for solving a particular problem. There you go.